moving charge. So that's why we picked the insulator. And also my lecture today is kind of try to introduce, what should I say, experimentalist agony of the how to get the result and how to interpret, and sometimes your nature never goes as you want it, right? So how are we going to make a piece out of it? And that actually, in fact, magnetic thermal transport in magnetic insulator illustrating so well how are we going to deal with the frustration in a just not only in the lab but also just the daily life. So that's what I'm starting. This one is one of my favorite quote about the any heat and temperature. So my third grader son asked me what kind of experimentalist I am. And one thing that I'm telling him open is I'm really good at measuring temperature. And in fact, I'm very good at measuring temperature. And he always confused with the heat flux. Feeling hot is like, he feels that is like, or feel cold as a temperature. But in fact, that's our body is very sensitive to heat flux rather than temperature itself. In fact, our body is like pretty bad temperature. I never tell my son it's like having a fever or not. And so it was like very, so I need a thermometer to measuring it, right? So this is like, exactly how you actually intuitively feel how heat is like transported one way to another, either pass from lead and some part of your body and everything, right? So with that, interesting thing in physics is how heat is conducting in magnetic insulator. And again, in my talk, there will be no second quantization operator or whatsoever. These are all about, I really try to give you some idea how this thing is measured. So when you actually write down the Hamiltonian about it, about the heat transport, you will actually take into account what has to be carefully looked into that before to take that data as, true. So this is like, we've been seeing this like so many times. This is like antiferromagnetic spins are sitting on the lattice. This is the basic, very, very bottom, foundation of the how we write down the Hamiltonian. And this is like the simplest Hamiltonian we can think of, exchange Hamiltonian and just the nearest neighbor considering. And this is like when we ordered, it's an antiparabolic ordering. And then always there's like many ... in the parentheses. And that including all the things that we don't want to think about, or we don't want to, this is not important for my model, okay? And coupling to lattice, coupling to conducting electron, but thankfully, as we're dealing with insulator, we don't have to worry about that. And father-labor interaction, that's very much important when you're actually looking at the spin wave spectrum. And multipolar, not just the dipolar, quadrupolar, octopolar interactions. And external field, for example, is also inside of the ... right? So simply thing is like applying external field, and then you actually follow this Zeeman Hamiltonian, and then applying this field will actually make the spin polarized with the field, and then we will get the finite magnetization and how that magnetization responds to external field that gives you susceptibility, which is like one of very fundamental first derivative and second derivative of the free energy of the parameter that we quickly measure. You can easily calculate very, and then, bar magnet in our refrigerator is attracted to my refrigerator surface because of this phenomena, very tangible, okay? But then, always I have a problem that theorists or even myself, simply writing draw the sticks are a lot easier than drawing this, right? When you think about the spin and the lattice, this lattice, okay? That connection never be a rigid stick. You have to always think about that spring of the lattice, because in reality, in real system, there's no spin attached to this ever, okay? So this, once you take into account, this is an even very simplest possible Kittel's books, phonons Hamiltonian. It got a lot complicated very, very fast. So first of all, very naively thinking, your exchange energy here can be maybe short range interaction. So if this spring is like contracted, this might be slightly larger. And then, it's all local, okay? Getting smaller. So there's like some modulation can be easily happen. Okay, so you cannot just think about the spin as a spin plus rigid lattice. It always, when you deal with the real system, you have to think about this way. And then so phonon, just to even remove the spin, your phonons are carrying heat energy and determine the elasticity, how sound wave is like traveling along here. And then of course phonon has a very measurable, very tangible momentum energy spectrum dispersion relation. And then something that I want to convince you for this lecture is phonon is always think about, oh, we don't want to think about phonon. Oh, phonon should not be important because we're very low temperature. That is actually not true. You have to be very, very good argument and convince yourself that why phonon is not important. So I really want to emphasize that phonon is not always bug, but it actually feature that all the experimentalists, for example, yearning for the smoking gun experiment for checking the quantum spin liquid. And, we do all kind of poking the sample with the neutron, lights and everything. But in the end, phonon is the one who right next to spin. So why not? We actually try to figuring out the way up to getting a phonon where any exotic spin excitation is ingrained onto it, right? So that's a kind of motivation here why we study the magnetic insulators, okay? Again, magnetic excitation itself, of course, carries heat as well. So this, again, I back to the rigid rod connecting the spin again. And then you actually have this like spin flip excitation that can actually move next neighbor, especially in 1D. And of course, this pair is like excitation, and then that actually carries heat. So I'm not completely discrediting that this is not existing. Phonon is more important. And you have all of this phonon, and on top of that, you actually have to detecting this. And then in order to do that, there's like many excitation can carry heat. In the end, how are we going to distinguish what kind of parameter can actually giving us different behavior to distinguish one is from the phonon, one is from spin, or one is from, here I describe here, non-mobile excitation can hybridize with the phonon. So if you think about just the local spin excitation, that is just the only happening locally, but then when they actually see the phonon, they can actually only riding a phonon's back, they can actually move out, and then they can carry heat. But what kind of particle is that? That's not spin, that's not phonon. So we really have to come up with this kind of new way of to think about how heat transport, not just the only interesting part and non-interesting part, okay? So how are we going to distinguish this origin? So for that, my lab is doing a lot of the heat transport measurement. And less probably, I'm do a lot of the detail about how measurement is done. The more theorists understand how measurement is done, the last question I was going to get when I showing some data, oh, why don't you measure the summer Hall effect? And like, okay, why don't I measure it? Why don't I measure it? And I'm going to explain to you why don't. I mean, I'm still trying. I'm still trying to measuring and always getting some data, but I'm going to try to kind of talk to you why I don't measure it. Okay. Okay. So this is like how you actually measure heat transport. You actually have your sample, preferably long, okay? And then hopefully along this direction, there's no significant anisotropy. That's what we assume. And then heating the one side, so you actually put it in constant heat. And then bottom here, you constantly leaving the heat is leaving. So you're like not equilibrium state, okay, by no means, okay? This is like so-called steady state. So your temperature, once this gradient is established, heat is constantly coming in, heat is constantly leaving, but gradient of heat inside become 0, right? And especially when you pick up this very middle steady state or quasi-equilibrium state, delta T, dt dt. So time derivative of temperature goes to 0, okay? So that's our setup. And then what we need is, so the heat is going in, and then, so summer conductivity, like last week, we had Brandon gave such a plenary, very comprehensive, lecture about the summer conduction. And this is like the Fourier's law. Your heat current x direction, I'm going to call this as x direction, and then temperature gradient along the x direction, that coefficient is thermal conductivity. Okay, so how this is measured, I actually get the thermometer, one here, close to heater, hot, and bottom here, cold, and then I measure delta T, and then I actually kind of Brandon's Boltzmann transport theory, put it into very cartoony way so that I can actually explain this to undergrad as well. So this is like how we're actually going to do it. So infinitesimal temperature gradient here is whatever heat carrying particle. That heat carrying particle can be phonon, can be magnon, or some very exotic some excitation. Okay, and then that is basically T minus T plus Vx over here, and then that's actually written as a dt dx. So often this minus sign is because coming from the vector is coming this way, but then temperature gradient is like hot minus cold. That's why we always put this minus sign here, okay? And then we can actually think about how much energy required to increasing temperature, this reason by delta T, that definitely including the specific heat of that heat carrying particle. It can be magnon's heat capacity, phonon's heat capacity, okay? So that's what this is. And then I just plugging in delta T instead of the over here. And then finally, you can actually write down the how much energy across the going through the unit area is that energy density multiplied by that velocity. And then that will give you this thermal conductivity being proportional to thermal conductivity, heat capacity and square of your particle velocity and the relaxation time, scattering time, that would be. So that's a simplest way. So this is like open, or actually combining the V and tau that actually corresponding to mean pre-pass, that actually going the distance without any collision, significant scattering, and that's how your actually thermal conductivity written. And of course, we can actually use it for more serious, counting all the mode number and different dispersion. That's actually how phonon thermal conductivity can be written. Exactly. Phonon velocity, this is like by acoustic mode velocity V constant, so it's a K independent constant. And then we do all this trick that, take this substitution of the variable, and then we can actually take the integration up to divide temperature, and where the K linear velocity is like still hold, and then we can actually get the temperature dependence of the kappa. Okay, and here heat capacity, this is like any bosonic density can be going in here, and this is like also within a Debye model we can actually get the Vs, or we can actually measure Vs pretty well, but this one, relaxation time, has a very little handle on it, okay? So if you look at this book, this is like written at the first edition is 1973. And this book is like still, I think, not only me, but many people's great Bible. And you can actually write down the scattering time into various scattering process, like boundary scattering, point defect free scattering, Unklapp scattering, and normal I forgot the one term, normal scattering. Normal scattering is like just the momentum preservation, and then Unklapp scattering is including the distance, the amount of the crystal momentum. And these parameter has all kind of parameters, and then you can plugging in. And if you calculate the phonon conductivity for very clean crystal, it usually have a low temperature, T cube dependence, and then high temperature, it goes down to T inverse. Then you will actually have a phonon peak. And phonon peak's location is not anything, it's the two. You can think about this as a phonon scattering increasing because of the heat capacity is increasing. And then once you go down here, it actually scattering effect is like taken over. And then eventually it got to flatten up very high temperature, okay? So if you look at this is like diamond phonon band. So this paper, surprisingly, 2009, when the quantum espresso was become widely available, and then they actually calculate this, and then this data is measured with the elastic neutron scattering, the inelastic phonon neutron scattering. And then they are actually doing really good job. And then in here, they are directly solving that Boltzmann transport equation that Brandon showed last week. And then they actually get these number, B, D, and all those things that you can actually calculate from this number. And in fact, it was this paper is emphasizing that on top of this, they have to add this acoustic mode and optical mode phonon scattering count is very important. And whatever they do, look at this data. So there's like two data from 1000 Kelvin to 100 Kelvin, two kind of the diamond thermal conductivity they measured. And one is naturally, this one, the bottom one is naturally available, the diamond. And then this one is you actually enrich it, diamond carbon 13 with a carbon 14 certain amount. I forgot how much amount. And then when you actually take into account the mass difference, you can actually get this two curve, which is like amazingly doing well, okay? So this is a great example of this. But if you look at here, if you have some unknown material, unknown amount of the disorder, unknown amount of how clean the crystal is, and etc., and then you measure the thermal conductivity, which is usually have a big peak and then come down, and then you try to fit this data, and then this data has, even though you actually know what VS, the speed of the sound, this actually has a many fit parameter. And it's kind of, if you have a many fit parameter, a simple curve like gently rise and then gently coming down is not that hard to fit, right? So for example, this is like one of the example is the ruthenium trichloride is, this paper came out 2018 and claimed that everything is phonon, which I mean, I have no problem with that. And the way, I'm just to show how data is like analyzed, and is that they took the data all the way to 400 Kelvin, and then they fit to this, actually I actually leave out another term here, Tn, the normal scattering term, and then they fit all this high temperature. By the way, that was like pretty kind of gentle because ruthenium trichloride, some of you may very well know, it's a very thin layer structure, and then it has a very, a lot of the stacking default. And because of that, the phonon thermal conductivity of high temperature is relatively flat, okay? And then you can actually do this. And then there's like strong field dependence. And then they actually introduced this term, tau mag. And then this tau mag, the relaxation time arising from the magnetic scattering, they actually have an empirical form of this kind of shape. And then this 3 comes from the phonon's mode number. And this is like kind of almost like some kind of probability kind of looking function. And then they fit this data very well. And then since it's a fit very well, phonon scattering from the magnetic impurity, I mean, there's like some physics going in here where the onset of this scattering is like starting, that's and so on. But it actually fits really well. And then this is like ground for most of the thermal conduction in ruthenium trichloride is happening at based on phonon and so on, okay? So that's what it is. And multiple of the paper is like actually analyzing the data is like mostly coming from phonon. What's the deviation? How are we going to explain the deviation? And most, like easy to recognize this contribution would be this kind of magnetic originated scattering. Okay. So with this, I'm actually, since there's like a lot of this how to interpreting data is data, right? I mean, you measure, if you have a good experimentalist, your data will be confirmed by other people, right? And data is data, but how to interpreting is really, what should I say, personal taste or who you are friend with, right? Or, what kind of theorist, what type of the theorist you're next door, and so on. So this is like just a really, I mean, so to me, I just want to really make this talk is about the data and how to take the data, not about the interpretation, okay? So I'm going to tell you about how to measure thermal transport, how to prepare sample, and what are the temperature. In the end, what we're measuring is temperature, what kind of sensor we're using, and how do we know the sensor is good, right? And condition and measurement. And then why thermal Hall effect is excruciatingly hard to measure. And I kind of tried to go over it. And, don't just, I mean, I know you guys serious work really hard too. I mean, but thermal Hall effect, just really my sore spot. Then if I have a time, I just want to just introduce this, our toy model we recently came up with, the how phonon interact with the spin degree of freedom. In this case, just make it everything simple. I'm just thinking about the single ion spin, okay? So there's no J. J is like so small. So then still single ion physics can interacting with the phonon. So for example, when you're applying field, you actually have a Zeeman splitting. And single ion can be just the one from lower Zeeman splitting, Zeeman level to upper one. That's just locally happen. It's nothing to do with magnetic ion talk to next to. So there's like no J. However, if they have actually interacting with the phonon, what happens is at finite field, you have a finite Zeeman gap, and then your phonon has acoustic phonon. Just we are not worried about John, just the acoustic phonon. And then they actually share the eigenstate, and then they hybridize. That gap is going through h square. And then now once you have this is like neither phonon nor spin flip excitation. This is like kind of hybridized particle, has a two band. And then if I take the derivative, this with velocity, of course, if you're increasing the field, it will go up here, and then the gap is like even higher. So dispersion will change as function of field. Since dispersion is changing as function of field, also that will changing function of your velocity is changing. So let's assume the previous kappa equal CV squared tau, and if we kappa is CV squared tau, and let's tau is like very complex quantity. I'm not going to touch it. Just to keep it constant. Even so, we can actually get from V is like changing. We can actually get the kappa will have field dependence, completely localized spin, and only hybridizing phonon. So this is like this. I think this is like our model, and this is like how we should think about how phonon contribution. Phonon is kind of hybridized with the spin degree of freedom. Okay, so let's start with how to measure heat conduction. So this is like the cartoon picture I showed to you, but this is exactly how we measure in the lab. Okay, this is like cartoon picture, but this is like our measurement. And we actually, instead of the fire, we actually using the about very small chip resistor. And of course, chip resistor is like very carefully in situ characterized. And if you're applying resistor, applying heat, current, then it will creating Joule heating, I square R. And then that heat is all going into sample. So near the heater, temperature will rise. And then sample is like very well anchored, very well. Well is very important part. Anchored to the summer bath. So all the heat going in has to be leave the bath. Okay, and then we measure two temperature here. Here, the important thing is that your heat current has to be mostly one-dimensional. Okay, that means your equi-temperature line will be parallel to this perpendicular, this like horizontal line. Okay, so if you measure from here to here, this will be same line, just a parallel line of the temperature. This is like very important when you actually measure the thermal Hall measurement because they will not have those parallel temperature line. Okay, so typical dimension of our sample, magnetic insulator that we studied, ruthenium trichloride, all kind of magnetic insulator, is this area on the top is about 20 micron to 100 micron thickness, and then width from here to here is like about 0.1 to 1 millimeter. It's a very small, okay? And then length, if we have a 3 millimeter sample, we had our day. I mean, that's 3 millimeter sample, and then if you cannot measure your thermal conductivity, I mean, that's just that should not happen, okay? So here, LTH, I actually define as distance between the two temperature. And that is usually kind of similar order of the similar size of the L or slightly smaller, maybe like 80% or 50% and so on. Below the temperature. So we measure temperature difference and then dividing by this length scale, that will become gradient of the temperature. Yeah. Yes. I'm getting there. Yes. Yes, of course, that's the most important thing. So here, thermometer is most of the research group in the world using either thermocouple, and I'm going to go more detail. So thermocouple is basically measure the DC voltage, and then you measure getting out of the temperature. Okay. Resistive thermometer is again similar metal film chip, and then you measure resistance, and then you convert to T. So these two, I'm going to actually spend some time a little later, okay? So with this, we can actually calculate thermal conductance is how much you heat put it in and how much temperature gradient you're getting out. And then you're plugging in some appropriate dimension, sample dimension, you can get the unit of watts per meter Kelvin. That's the thermal conductivity unit. Yes? Oh, yes, I'm also getting there too. How good a vacuum? So I give you a number, our measurement is like at room temperature about 10 to minus 5 to 10 to minus 6 torr. And once you go down to low temperature because of the cryogenic, especially below nitrogen temperature, we expecting to be a lot higher than that. Yeah. Yes. I will mention that. And then here, most important thing is we're actually probing very low energy excitation, especially if you think about the phonon case, that's actually the dispersion starting from K equals 0, very low energy. So most important thing is whatever temperature gradient you measure has to be much, much smaller than your best temperature. Right? So for example, if you do this measurement, so empirically, we keep this delta T is 1 to 5% of the best temperature. Okay? So if you measure room temperature, 300 Kelvin, 1% is 3 Kelvin. So that temperature gradient is like 3 Kelvin. But if you think about it again, humans, we think that we're very good with the measuring temperature, but we actually not. So if you think about this sample to be 1 millimeter, okay, temperature gradient is like 3 Kelvin. That's enormously high temperature gradient. Okay? So, but that's 1 to 5. There's like there's no theoretical justification, especially when whenever this and this is I give you linear response, which means that when you're increasing heat, your temperature is linearly increasing. However, when you get to the nonlinear response, that's already so late, right? What happens is when you have a nonlinear response, my delta T is so small, I want to actually cranking up my heat current and then increasing more temperature gradient. What will happen? Yes, burn or entire thing, including the summer bath, the whole temperatures goes up, right? So you're actually, let's say your measurement is like 3 Kelvin, okay? And then 1% of 3 Kelvin is 30 millikelvin. I'm supposed to maintain 30 millikelvin temperature, but oh my God, it was so hard to measure. So my student cranking up the heater current a little bit, then whole thing, even or my helium bath and everything, temperature goes up. And then at that point, you're not measuring thermal conductivity at 30 millikelvin. You're actually thermal conductivity moving from 10 Kelvin to 12 Kelvin, around that. So because of that reason, I'm very, it's my opinion, so I may be wrong. But as of now, I really think that nonlinear response of the thermal response is like very, very high, very, very hard. Because if you're not nonlinear regime, it's very hard to check. I mean, of course, we're always monitoring summer baths, but usually, I mean, this is like very exaggerated. Your summer baths mass will be probably like 10,000 times more than my sample's mass, okay? When that summer bath temperature start going up, you're deep trouble. That's too late. That's what I'm getting at, okay? So anyway, the number is like 1 to 5% temperature gradient. And then also, another thing about the thermal conductivity is it's not just you actually measure everything. Mostly phonon, right? And if you're measuring conduction electron, it is actually conduction electron too. Magnon and any other something that you wanted to see that will be maybe buried inside of your signal. Okay, and so often people write down since this is conductivity, you can actually think about multiple channel, and then that channel is like adding on it, but that not always, this is like not talking, this is not talking, that is not guaranteed. Yes? So that's right. So when this range is just, we always checking. So I'm going to show you the data and make sure that it's linear. Okay. So as I said, nonlinear, once you see the nonlinear behavior, that's like most of the time is because of your entire sink temperature is going up, entire setup temperature is going up. So I'm not saying it's not impossible. I'm saying it's hard to, you have to be extra care has to be taken in order to distinguish heating versus nonlinear response. Yeah? Yes? I'm getting there too. Yeah. Mm-hmm. It's a DC. Mm-hmm. Yeah. I think I didn't think about that. I will show you just in a bit. Okay, so that's why external magnetic field would be very helpful, so that at least we can actually each excitation might have a different field dependence. Yes.
You say sample is very small.
Yes.
It's a total temperature difference. You don't care about the temperature gradient per distance.
Oh, so when we do that, when we actually calculation of the thermal conductivity is like temperature gradient per distance. Yeah, well, the reason is that in practice, most of samples are, range up to 1 millimeter to 2 millimeter. So this number within that, so, in fact, in my lab, I never measured sample more than 5 millimeter. So that delta T is actually more, tangible measurement. I can check right away before I start my measurement. That's why I'm giving that number. Yes, this number is absolutely depending on, if you have a like 30 centimeter sample, then this number has to be scaled to that. Yes. Yes. Okay, yeah, I'll show you. Okay. So here, remember, our body is very sensitive to heat flux, but in instrument-wise, we did not measure directly heat flux. What we do is we put the heat, what we think it is, and then we measure, and then all those heat is going into sample, and then we measure temperature difference. So input is heat DC current, but the amount of heat is like not directly measured. We just assume that, if this is like 1 kilo ohm, if I put the 1 milliamp, we assume there was 1 milliwatts is going in. And that's why vacuum is very important. And then we actually have to take the measurement output is temperature, and then we really understand our thermometer very, very well. Okay, and then here, this is like the box that that you guys ask. For the heater goes into sample, dissipate into the summer bath. Okay, but that's actually not true. For example, yes, there might be some. We thought there was good vacuum, but there might be some, let's say, some residual gas, and then that can definitely shorting the heat path. Also, if your temperature, the heater is like, hot object, and then it has a radiation. The radiation is proportional to T to the fourth. It's a very big number. So when you measure this way of the measurement, my way of the measurement, above the 200 Kelvin, I'm just actually really seriously taking into account of the heater radiation and what kind of environment you would have. So for example, your sample is very confined, small space that radiated heat, deflected back from your copper container, and then heating up the sample. So there's an extra heat source existing. So you have to really careful that make sure that your condition of all the heat generated, I square R, is going into your sample using the vacuum, appropriate temperature range, so that you don't have to worry about the radiation and many other things. Okay, and heat current maintain almost one-dimensional profile because that's very important. Otherwise, depending on what type of the heater you're using, if you measure here and then here along just across the line, horizontal line, if temperature is different, then what are we going to learn from that? And then third is like such a simple lambda size very much matter. So if you look at here, there's a lot of things is attached to sample, heater, thermometer, two thermometer, and then attached to the bath. So how well thermometer is like attached to the heater. When we measure our body temperature, we just put the thermometer under our tongue, and it was like pretty well attached, I would say. Also, in that case, entire my mouth and all heat capacity of my mouth, body mass, is much bigger than my tip of my body thermometer. So I think that's also small. And it was like very well attached. So how well attached? That's actually really important. So here's the real sample, okay? This is like ruthenium trichloride. This is actually sampled from the very old time. It's like 2016, 2015, around that time. So this is my sample. It's a 1.2 millimeter lengthwise, and width is like 0.6, and thickness is 0.06. And then it says not a great example, I said. And because we really try hard to measure the summer Hall effect. This is before that big summer Hall effect, okay? So we kind of try to see what it is happening. We just cannot measuring. The way we couldn't do it, here the thermometer attached it through the silver and then to the Sonox sensor, which is another Sonox sensor, so 3 Sonox sensor. The worst part of this sample was actually over here. The sample, and then this is heat bath, the attachment was really not good. So what happened is even small heat is going in, your sample entire thing heat up. So actually not showing here, just underneath here, there's a thermometer for heat bath, and then that is actually heating up really fast. And then the way we can actually tell that the sample to bath connection is not good, so it has to be gone. But I don't know. After that, we never take the good picture because when samples are working, I mean, I don't know, we forgot to take a picture, and usually we take this photo after we finish measurement, but then data is good, then we busy to analyzing, so don't take a picture. Yes.
You're coupling to the surface.
Mm-hmm.
So how do you know that it's not going to the surface?
Yes. So that is here. You can see this silvery thing. This is like actually silver. This is basically silver, powder silver, and that has like typically this sample. So that you should know about basic thing about your sample. So your sample thermal conductivity is like order of 1 to 2, 1 to 10, let's say, okay? And this thing, thermometer, this silver has like thermal conductivity of the 200 to 1,000, okay? So we assume that this from heater to connecting to sample, the connection is like much, much higher thermal conductivity than anything from the sample. That's why we actually assume that the heaters are going into. So of course, heat will be. So transiently, this heat, as soon as I turn on the heat, it will actually warm up, and then everything will become the same temperature. And then heat is like start flowing, right? So that's what we have to wait. So did I answer your question? Yeah, so let's look at this. Oh, so this is like how we measure temperature. It's like, I think it was like around 30 or 35 Kelvin. And you actually turn on the heater current, and then you increasing heater current. And then you might see this is like actually square root 2, every square root 2. So if you do that, your heat current is like I square multiplied by your heater resistance, which we also monitoring on time, okay? And then we can actually measure this delta Tx. And then, when heater is 0, this is 0, and then increase, 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 and then come down, okay? And then we can actually plot the Q and delta T, and then get the multiple data point, and then get the linear plot, and then that's corresponding to kappa inverse. I mean, this is actually inverse of the summer conductance or summer resistance in analogy to electrical conduction, okay? The reason we don't use the AC is you can actually see here at 35 Kelvin that equilibrium time is an order of 1 to 5 seconds. So if we're using the enough AC measurement, that has to be, whatever AC period has to be in the order of 10 seconds, which is like 100 millihertz. And we try those, it really, 2 omega signal was like at that low frequency. It's very hard to, we can actually, one thing that we did was, we are not using the lock-in, but just the measure, just the DC measurement, fast DC measurement, and then try to get it out. And then that takes a lot longer time, because you don't want to do just one period. You want to do multiple period and so on. So we kind of abandoned this, but that was always a back of my mind. Yeah, is that good? Yes? Mm-hmm. Yes, right.
How do you do that for temperature?
We don't do that. So we just do it on the DC. So this is all DC current. Yeah.
But even if you apply AC current, you won't be able to with the higher.
If we do the AC current, we'll just see the transient behavior because equilibrium. So we want to measure we want to measure thermal conductivity when there's like no divergence of the heat current is zero, right? Heat current is always there, but divergence has to be zero. So all the coming in has to be all the come out. But that's actually just that time scale. Electrons are reacting a lot. A lot. Because this involving the heat capacity, the heat capacity of the thermometer, sample, wires, and everything is connected. That's why. Yes?
It's like for this heat bath is in contact with some like silver.
Yes.
Previous picture, it seems like it's some G bars.
Yes.
Is there a reason why?
That's right. G varnish turns out to be really bad connection. Very bad. Yeah. Okay. Yeah.
Faster. Why the contact is bad?
Because if coming in heat does not leave fast enough, you have to be same rate. How much coming in heat and then leave the heat equal. If it is leave the sample slowly, what happens is heat is accumulating inside sample that will increasing the entire sample temperature. That's right. Yeah. Yeah. So sample temperature is the one thermometer. This is like out of focus, so we cannot see it. One thermometer is here. The other thermometer is like over here. Yes. BAS is like BAS is like much larger than sample. It's a kind of canonical assumption, right? You have just a little bit of heat coming in. Your heat BAS is like much larger, much bigger, much conducting. Very high precision copper, so you can actually take it everything. Yeah. Okay. So this is like how we measure. Okay. So now thermal Hall effect. Okay. Thermal Hall effect is actually in terms of the measurement, it's not that different. But what happened is, so thermal Hall effect is heat flow resulting from perpendicular temperature gradient, and it actually is like known as the Ricci-Rodak effect. If you look at the Jiman's book, that's what he actually said. And then it only, according to Angsaga's reciprocity, the only happening when the time reversal symmetry is broken state, right? So this is like how thermal Hall measurement is done. Here you can actually have so these two are two thermometer we had before. And then now we have this is like heat current is this way, and then magnetic field is like this way in this case. And then now temperature gradient is happening. Either C1 can be high or C2 can be high. That really, we don't know before we actually measure it, okay? So that's why when we measure longitudinal temperature gradient, this minus sign perfectly makes sense because that's actually heat is flowing this way, but then we measure this by this. That's why we actually put the minus sign. But when you actually talk about the transverse temperature gradient, that actually you have to be careful. So the way we calculate what we're measuring is two temperature gradient, delta Tx and then delta Ty. And then of course it has a corresponding length scale, Th and Ly, and then we can actually get the gradient, length independent value. The way we calculate the thermal kappa xy is using resistive tensor, exactly identical with the conductivity and resistivity tensor. So we define the electrical resistivity as a Tx over Ty, that's corresponding to rho xx in electrical conductivity. And this is like delta Ty over Txx, this is like rho xy, okay? And then we can actually using the matrix conversion, and that's how we actually getting this, okay? So that's straightforward. Once you have these two quantity, you can actually calculate that. But the bottom line is practically this ratio is about, so the delta Y is a lot smaller. Again, this is just all the data that, available data is at the order of 0.01 to 0.001, okay? If you do the full measurement. And think about that, let's go 30 Kelvin. 3 Kelvin, our temperature gradient is 30 millikelvin. And now we're talking about 0.3 millikelvin temperature gradient to even smaller, okay? So now that can be very problematic because you are using liquid helium or, basically liquid helium cryostat. And then you have a particular temperature stability. In order to reach, let's say, 3 Kelvin, you have to do, just 4 Kelvin is not enough. You have to go lower. So you're pumping some helium. So helium is like ore pumped, and then like its boiling temperature go down to 2 Kelvin. And then from there, I turn on the heater, and then I'll actually try to stabilize temperature. For the electrical measurement, about 1 to 5% temperature gradient, this is like excellent temperature maintenance. But when summer measurement, we have to exclusively stable temperature during your measurement. Not to mention, when you do the summer hole measurement, you actually have to sweep the field, right? When you sweep the field, again, if you constantly sweeping for a while, that will be okay. But when you start the sweeping, dBdt, like field derivative of the B is non-zero, that creating all kind of eddy current heating. There's a huge, so typically that's order of 10 to 30 millikelvin, which normally it's not a problem at all. But here we're talking about 3 Kelvin and 0.3 millikelvin to 3 to 0.03 millikelvin. Millikelvin stability, that is extremely, extremely hard to achieve, okay? All right, so that's how, of course it's simple. Why you're not measuring thermal conductance, thermal Hall. One of the major failure mode is it's very, signal is small, and delta Ty is like small, and it's very hard to maintaining the temperature stability during the long time the field sweeping. That's the primary reason of why thermal conductivity, thermal Hall effect is hard. Also, as I said here, when you measure thermal conductivity, the temperature gradient is linear. But now, temperature, if I draw the temperature profile, it will be actually look like this. Okay, so this is a kind of, this I draw in the cartoonish figure. So you can see the thermal line is over here, but then you measure here and here. That can be very, temperature delta Ty can be very different. Let's say your signal has to be over here, and so on. Okay, so that's something you have to very think about how you actually model it. And then nowadays we have a lot of the computation power of the comps or some simple thing, but it's actually when this thing happened, that particular heat carrier moving the other direction. So it is very hard to entering into the heat equation, in some normal way. So that's make the things a lot harder. Yes. That's because, we assume that because when you have so in principle, if your sample is already magnetically ordered, that's already TRS, broken state. So it, in principle, should have some more. You measure at zero field, you don't know where it's coming from. Is this really, so you actually do the field along the positive field, negative field, is that really odd symmetry or not? Those kind of things has to be checked. That's why magnetic field is like very fundamentally required. That's right. Yes. Yeah. Yes. Of course, yes, we do that all the time. So you seldom use, my group seldom report one sample, and this 2 sample has to be, to our very best, we made the sample exactly identical way, exactly identical, Sonox and everything. So yes, of course you should do that. But it's in low temperature environment, it's very hard to put in the exactly same thermal environment. One is applied field, one is not applied field. It's very hard. So either they're or, you basically measure 2 samples. So control is like, one is field on, one is field off, that you cannot measure simultaneously, right? When field is on, that whatever, I have to use the liquid helium, cool down, and then down there, field is on means everybody experience field. Is that what you're asking? Yeah. All right. Yeah. So you have to measure more than one sample. That's for sure. All right. Okay. All right. With all this, I want to actually, so all we measuring is temperature, delta Tx, delta Ty. So what kind of sensor we using? This is like, there's like 2 sensors. One is thermocouple. I mean, I just say type E because type E sample, type E and type A. And type E is particularly comes from the two material. One is chromel, which is like 90% nickel, 10% chromium. And the other one is Constantine, 55% is copper and 45% is nickel. And then they actually weld it over here. And this wire, we're using type E because type E comes as a very, very thin wire. It used to come as a 1/2 mil wire. That means this point where we actually detecting temperature is very, very small, which is great because it's easy to contact. It will be small amount. It will not take up a lot of the heat capacity and so on. And then so these two are very well-known thermoelectric material. So you have a known temperature, T best, and then from here to here, there must be some temperature gradient, and here to here, temperature gradient. But because of the two materials are different, their thermoelectric coefficients is different. So they have a slightly different voltage between here and here, between here and here. So we measure that voltage difference, and then we can actually measure temperature, right? So that's actually, this is like very handy. Many people use this thermocouple because, it's just so light and small and everything. However, also, of course, that calibration is available, NIST actually do the calibration for us, okay? So there, you can actually download the calibration all the way down to the 4 Kelvin, and the calibration is available, and we can open from time to time checking. About 10 years ago, there's a lot of the variation, but recently, I don't know, things are really on top of it, okay? So this is calibration. As higher field room temperature, you have about millivolt, and then you can come down about 3-ish. You actually go to minus. I mean, this is like not very good reason to use because voltage is like almost 0. But I'm actually mostly interested down below below 100 Kelvin, which is great. This is great. But important thing is not just the voltage. We're not interested in temperature. We're interested in temperature gradient. How much sense, because we measure small delta T. So we actually want to know what's the dVdt. When 1 Kelvin changing, how much voltage change? This is like, sensitivity. And sensitivity is like dropping. And then by the time you reach the, actually, this cannot be right. Actually, this axis cannot be right. Yeah. Anyway, sensitivity is getting small, and then about lowest number is like 0.01 millivolt per Kelvin, which sounds a lot. If you're actually used to DC electronics, 10 microvolt is easy to measure. But remember, at this around the come to the this, our delta T is much smaller, 0.03 Kelvin. So this voltage become very, very small, actually. So this actually great sensor, but I'm actually not thrilled to using below 10 Kelvin. Also, you can actually guess from the 90% and 10% chromium, this thing has a very strong magnetic field dependence as shown here. I mean, you can actually see multiple. So these are two different thermocouple calibrated. Actually, this one and this one calibrated. That's exactly same NIST calibrated thermocouple, but they have a very different dependence. So often people who are using the thermocouple, like the Shelbrook group, they actually calibrate fixed field and then calibrate along the temperature, just using that calibration, and then do all the different field, and then using the calibration. So the calibration is very important. And especially also when you measure the temperature gradient, you're actually using two thermocouple, and two thermocouple must have a same temperature dependence and so on. So, but this is like very big temperature dependence. I mean, look at this, like, percentage-wise, it's actually really not so great. Even higher temperature, like let's say 30 Kelvin, 5%. I mean, 5% sounded small, but when you translate into such a small temperature gradient, it's actually not feel safe at all. Next thing, what we're using is Sonox sensor. Like a lot of experimentalists are very familiar with the Sonox sensor. Sonox is like just the name of this company. Oh, where's that? Lakeshore creating. It's some kind of metal film. It's like lead and palladium in it, but exact content is like, what is that? Business secret, proprietary information. So nobody knows what's in there. Okay. However, it actually have a superb performance. And here, all these sensors are Sonox sensor. I mean, it's hard to say. You can actually see this dark black line here. That's the Sonox sensor. And this gold finger is like for the making contact. Okay. And it's actually size-wise, it's like I wish it was a little smaller. They're actually under the sapphire substrate, which has a very high thermal conductivity. And then underneath, there's a gold film on top of it so that it can actually easily make a good contact with the sample. And so these are size. The width is like 0.7 millimeter, not that small. You know, remember my sample is like order of the 1 to 2 millimeter. And then thickness is like, what is it, thickness 0.2 millimeter. So my sample is a 1 millimeter. I just cannot put, that's why it actually connected with this and then very fat, this is like this fat silver wire, and we actually attach to it so the heater can, the temperature can be read. The way we can actually be able to do this is, and then here actually Sonox is not lying down, it's actually standing. That's why it's out of focus. And so only touching this area on the sample. Even so, you can actually measure temperature because it has such a high sensitivity, particularly low temperature. So this is like, again, also, I copied from the Lakeshore, but we never trust, I mean, so this range is, the company said this will be the range of the each kind of model, but we do our own calibration. And then you can see from here, below 30 Kelvin, your actually resistance is changing almost exponentially over there. And here you can actually see, some people might be able to see one red broken line and blue line is like on top of it. That's the thermometer we're using together. So as a pair measuring hot and cold, and they have a very, very similar temperature dependence. When you have this similar temperature dependence, that means, you know, Sonox is like just a chip, right? I mean, these people just deposit 6-inch wafer, and then they cut tiny, tiny pieces. So if chips are right next to each other, those qualities are exactly the same. So hence, your temperature dependence and field dependence are very, very small. So it's actually choosing this pair of the Sonox is like my students' greatest job, one of the greatest job, okay? Like what, oh my God, which one pairs better, right? Because that's actually eliminating very much our calibration effort, okay? And then not only R versus steel, as I said, it's actually sensitivity is really important. The reason I can instead put the Sonox, you know, that's a gold pad is like this, Sonox is basically this Kleenex box shape, but then I actually only touching the sample on the small area of the sample, I able to do that only because down here, low temperature, the Sonox resistance change is like so dramatically, exponentially changing. Small temperature change translated into large resistance, which is like best for the measurement purpose. That's why we're able to do that. Sonox has a great, I mean, not great, but hidden weakness is actually not free from the temperature, magnetic field dependence. So these are just, again, from the Lakeshore. But if you look at here, Sonox 2 Kelvin, delta T over T is about 1%, which is like alarming. Because as I said, delta T, the temperature gradient we measure is over order of 1%. And if you're applying field, you actually create, even though there's like no heat current or there's no temperature gradient, only because of magnetic resistance of the Sonox that actually look like have a temperature gradient, right? I mean, that's should be difference, but this is like the same order of the magnitude that we are actually using as a measurement number. So that's why, again, you know, just without exaggeration, more than 30–40% of our work time is actually spent on the calibrating the Sonox before the measurement, after the measurement, before the using the measurement, during the measurement, all kind of things. You have to be obsessed about how actually well you can get those numbers. Okay. Okay. Finally, I just wanna. This is like the again also from the Lakeshore. I don't know, serious if you actually wanna start the somewhat conductivity measurement as a hobby. These are all your nice thermometers. But you might the reason I'm showing here is that performance in magnetic field, good. Not recommended, not recommended, fair above 60K, fair above 30K, okay? So this is like manufacturer's recommendation. That means I can translate maybe 1K. This is like, this might be okay. Absolutely not, absolutely not. Not recommended and above 60 Kelvin, not recommended above 30 Kelvin. That's how I actually interpreting it. So that's, yes?
No question. So, by the calibrated or not?
No, I'm not buying. I mean, first of all, it's a very calibrated one. It's like very expensive. Second of all, anyway, I would not trust the people's calibration.
I think the quality is pretty similar.
Oh, that really depend. Yeah, quality. Yes, quality would be similar. That's yeah. But I want to actually mention here, there's a many other thermometer because I actually spent a lot of time actually study the Johnson noise. So my plan was to put the metal junction on top of my sample directly, so that it would be excellent thermal contact and very small mass, and then measure Johnson noise and then measure thermal conductivity. That was like kind of my dream, and that actually didn't work out very well because this kind of crystal that I showed you, aluminum. So the plan was I apply aluminum, and then aluminum oxide, aluminum junction, and then I measure the junction, Johnson noise. I just cannot deposit aluminum film on top of this crappy. I mean, even though it looks very shiny and beautiful, aluminum just didn't like it. Okay, this is like the 60 cobalt radiation anisotropy thermometer. Anyone heard of? So my former colleague, who I inherited his lab, he has this setup. So this is like, cobalt 60 is, like radioactive. It's actually emitting gamma ray. Okay, and then you can put that tiny piece of that cobalt 60 right next to your sample. And then you, outside of the fridge, which is room temperature, you actually measure the radiation coming out from the gamma ray. And then their anisotropy of the gamma ray emission is changing as function of temperature. So you measure about half circle of not half circle, just about size of the detector is like this much. And then you actually see the how much anisotropy is changing. And then using the Boltzmann factor, you can get back out the temperature, and then you can actually get absolute temperature. And then and same for the Johnson noise, it will be very little field dependence. And these are dream, but so can you see that what's the difficulty? I mean, you have to go through probably 60 or more signature to put the radiation element inside of my fridge, and forget it, I cannot use the National High Magnetic Lab, and all kind of thing. And so on. And then capacitance thermometer is also, these are also very working on relatively narrow range, except for the Johnson noise. And they are very specialized thermometers. So there is way to calibrating it, but that's not very common. Yeah? All right. So with all this, oh, yes.
Maybe
yeah.
Before you move on, so
yeah.
you mentioned you did try this Johnson noise?
Yes. Mm-hmm.
And was it going to be a local temperature measurement?
That's right, local temperature. Yeah. So this is sample. I can deposit the junction up here. As if I attach the thermometer, I can just one here, like that.
Well, sure, but I
yeah.
think like,
yeah, it will be local. Yes.
Okay, it's half-baked question, but
yeah.
I know like Brian Skinner, people like this have done some theory about
yes.
You should be able to get temperature maps.
Yes, that's right. Yes, if it worked, yeah, that was whole idea. You can actually, why not? Why have a two? Why have like 9 of them, right? Array of the thermometer that measure entire profile. Yes. Yeah. Yes. But I mean, I don't know. There's, things are, as Philip said, electronics get a lot better. So I'm waiting for my time still but hopefully before anybody else doing it. But capacitance thermometer is another very bulky thermometer. So this is like actually capacitance. The silver. So silver is a very the silver measurement, but this capacitance measurement, the signal size is like size of the. Because of that, it's size dependent. So capacitance thermometer is like really bulky. And that's how, so we measure capacitance. And then this is only also working below, below 4 Kelvin. And then little field dependence. So people try to calibrate one thermometer against this capacitance thermometer, and then try to using that thermometer is like the master thermometer to calibrate next one and next one and next one. Yeah. Okay. Now with this, let's go and look at interesting examples of the thermal transport data. And of course, interesting is purely my personal. Okay, it's like There's like so many other thermal conductivity data and everything, but I just only choose these things because I have a personal attachment, okay? So this is like ET, ME, SB, PD, DM, IT. So this is like triangular, so this part, PD, DM, IT2. This actually forming the triangular lattice and organic material. And in 2010, it has a very famous figure of the thermal conductivity figure that here, look at this, kappa XX divided by T versus kappa square fit. So if you look at over here, thermal conductivity at very low temperature, let's say tau is constant. C is like basically how many heat carrying particle, either it's a phonon or whatever, is actually coming. So the way open people do is like C, phonon heat capacity has like T cube dependent, and this is like roughly T cube dependent as we saw in the phonon case. And then you plot over T versus T, that linear line is coming from the some phonon. And then when you actually extract it to 0 temperature, there is like actually non-zero intercept, right? So that is interpreted as due to the gapless fermionic excitation. So this must be because of the frustration of the DMIT. And then when DMIT 131, that's actually spin liquid, that's the pink. And then analog of the non-magnetic analog actually goes to 0. So based on this data, this panel, this is a claim as a quantum spin liquid and organic triangular magnet. And it was like really exciting because this is like actually not so small and really significant contribution from the fermionic T linear dependence of the thermal conductivity. What else can cause this? Because there's like nothing else we can explain this phenomena. It has to be gapless fermionic excitation. So it has to be some exotic, some spin-based excitation, okay? So this has been many people, including myself, aspirational figure. Oh my God, I want to find some material can show this, okay? Sadly, or I mean, luckily for us, 2019, this experiment is completely revisited by multiple group in here. And so this data was like not reproduced, okay? And then again, this data is corresponding to over here. And then all the other samples are just stay down here, including, so this is like the non-magnetic analog is like down here. And then all the samples are basically does not showing any thermal conductivity. I'm showing this data that, you know, this group did anything wrong. I'm not saying that at all. This, I mean, they are both, all of them are very reputable people and I dearly trust them. This example really illustrates how difficult the measurement is and how many things can go wrong, right? There's like many things, just a little bit of the, you know, didn't, you know, think through carefully can cause very different result like this, and like amazing of the discovery of the quantum liquid to, no, it was just a boring insulator, right? So it's actually really all I have to think about, the care about the addenda, environment, and everything. This is like conceptually easy measurement, but it can actually go wrong a lot of things. Yes.
Do you have any what could have went wrong here? Could it be this non-zero intercept?
I mean, since this is recording, I'm not going to say that, but I have a lot of idea what could have been gone wrong. So for example, you know, as mundane as how thermometer got attached, right? To so here you can actually see that the big difference of the, so both, this is two different group, and then all the new sample they made was all the down there. There are basically no thermal conduction, right? So if you think about it, having very small thermal conductivity is easy to measure because in order to have a small thermal conductivity, your temperature gradient has to be large, yeah? Right? So large temperature gradient is easy to measure. And this is like the higher thermal conductivity is meaning that it's high, but it's like, you know, hard to measure, right? Small. So I don't know what goes wrong. You know, there are very good people, and it's just a mistake because so many things can go wrong.
You want to go off the record? I can.
No, it's okay. All right. Okay, so this is like great. I mean, Again, it's a very aspirational. I just want you guys to know that this was a little become a controversial. Okay. Yes. Say that again. Yeah. Uh-huh. Yes. Yeah. So it's this is like some experimental kind of cutoff here, right? I mean, so summer conductivity. Right, summer conductivity goes to 0, unmeasurable, below noise level, before temperature reach 0 temperature. That's how you're going to interpret. This interpolation of this just meaningless because it's just the data was like looking a little linear. But if some of them are but at this point, I would say this one is just summer conductivity is so small. It maybe kind of come down as a more T squared dependence, maybe down there. It just they cannot go down below millikelvin. Again, this is like not easy measurement. If you go 70 millikelvin, 1% of the 70 millikelvin is 0.07 millikelvin. That temperature gradient is like very hard to maintain here. Yeah. Okay. Another example, again, ruthenium trichloride has, I mean, I don't have to, anyone who never heard of ruthenium trichloride? Probably not in this room, right? Proximity to type quantum spin liquid induced by applied magnetic field. So before this paper was, type spin liquid idea is coming out. I mean, ruthenium trichloride already have this because of the honeycomb lattice. That's actually why people got interested. I actually our group happened to work on much before that time, the alpha ruthenium trichloride, and then have this. The legend is actually underneath. Oh, what happened here? So we measure 3 samples. Never report 1 sample. Okay, don't trust just only 1 sample paper. They all have a very similar behavior. What happens is when you have a big peak, but then when you apply field, so this open and close is like goes the same. 14 Tesla, it's completely quenched. And then there's like big, like that little some feature in the low temperature region. Okay, and oh, there it is. Yeah. So these are 3 samples. They are very systematically similar value. And then when I measure the field dependence, so this is like offset, this is like delta kappa from kappa 0. I'm coming from the electronic transport property. This is like kind of corresponding to magnetoresistance. You're subtracting the resistance on field minus 0 field resistance and divide by 0. This is like actually doesn't make sense in summer conductivity because kappa naught has a lot of the kind of information that might still carry on the field. But we actually found that it has a very strong minimum and then increasing when you applying field, okay? And then the field minimum is stay constant, and then when you go even higher field, higher temperature, it's actually moving out, okay? And then if you look at this ruthenium trichloride, and then it's a kind of a far away cousin, which has a long range order, chlorine trichloride, the field dependence is like so different, right? And so with actually combining with the magnetic torque measurement, this is like the paper that we put out at what phase diagram would look like. So there's like something special region, and then there's like some very distinct region across the 0 temperature according to across the field. And then, I mean, we kind of hand waved about this might be some proximity quantum spin liquid and et cetera, okay? So anyway, this was like all before the famous, and then when this was out, and then I saw after a couple of years later, I saw that the organic data was like so different from the other people. So I was actually really waiting. Some other people were actually taking data. Oh my God, what if I'm totally wrong? And did I mess up something or anything like that? But luckily, we actually see like a lot of the values. Other groups, this paper was all about how many samples they measured. They actually reported like 4 different samples. There's like 3 of them are showing the picture. You can actually see the thermal Hall measurement, and heater is attached. And then they actually don't showing heater. The heater is go all the way. These are all the silver wire and et cetera, et cetera. And then all the values and field dependence, they're all same. So, thank goodness. And then, it was actually, good, okay? So this is like all before this famous figure of the thermal Hall measurement, okay? I don't have to explain this. This is like basically they apply outer plane in between outer plane, and so 45 degree here's this is 60 degree, and so there's like some in plane field and outer plane field. At that time, this was you needed some outer plane field in order to creating a Hall signal, and then we need an in plane field try to induce field induced transition, and this paper really baffled me because yes, you can actually measure as function of field. Thermal Hall measurement is actually very small, as you see earlier. The thermal Hall measurement is like order of 2 watts per something something, and then this is like 10 to minus 3. So it's actually signal is like very, very small. And then you can actually see field dependence. So something is increasing and flat and go down, okay? And same for the 4.3, something is flat and go down, something is flat and go down, okay? So the reason I was like really baffled was I absolutely trust this data that field dependence has come up and then constant and then go down. And then there's like some field dependence being constant reason. But that value happen to be this number. So this is like just the, thermal conductivity number, 0.88. So this is like now known as a two-dimensional thermal conductance quantized thermal conductance value. This value has to be exactly half of that is very coincidence. In a sense that this value, just the absolute value itself, can be depending on so many different things, such as what kind of thermometer you use, how big was your thermometer, and et cetera, et cetera. Okay? So, but nonetheless, the interpretation is like so attractive. You just cannot let go. How can you let go, topologically protected chiral edge mode of the Mayonnaise charging neutral Mayonnaise excitation? Oh my God, how can I let that go, right? So this was really good. So because of this work, inspired so many thermal Hall conductivity measurement. And now you also know this is like another. It actually this one showing that as a function of field. Now this is like field is like parallel to thermal Hall current. So this is called the planar thermal Hall effect. It's not like Lorentz force geometry, but when heat current and field is like same direction, you still get this phenomena. And then they would reach the this conductor special value around like 9 Kelvin. There's nothing special. And then this data was interpreted as this is like this thermal conductivity. Thermal Hall conductivity is originated from the bosonic topological Magnum band. Yeah? And then actually go back and you can actually look at this data as like supplementary info. You can actually see the 8.2 is like go above this. So data are actually consistent. And then values are actually similar range. So this is like 1. And this is around 8.4 is like, just about 10% smaller. That's actually very, very likely because of the way how you attach the sample, just the, you thought that you were using the small amount of silver paste, but it actually more than it was. And that kind of error can be actually causing all this kind of variation. But then actually two different interpretation. And then again, many, yes, yeah.
The fields though that we see these values that are quite different, right?
Yes, yes. So what happened here is that this is like the perpendicular field. And then so here is the parallel field, right? So the way these people done is field is like just the in between A and C axis. So you can actually look at this upper level. That's actually same as this range, right? This is like always like field is like along the AB plane. So it actually, this range and this range is like actually almost the same range. Does it make sense? And also, later I actually learned that, so this data was, especially this data is taken in Kyoto University, okay? Kyoto University has really efficient helium liquefier, and their helium cost is like less than $3 per liter. How much I'm paying, how much we pay then? We paying like $21 per liter. And this set of the data, one curve was taken each curve, so field sweep all the way to the 16 Tesla their magnet takes about 3 months. So they are basically taking very slowly lamping the field. I mean, actually not lamping the field. Stop every 0.01 Tesla and stop and measure, waiting for another 3 hours and measure many times, and then do it again and do it again. So this one sweep takes us 3 months. So the data look like, oh, field sweep from 4.4 to 4, but this was like more than 2 years worth of the data. And then of course, in between you have to transfer helium, then you have to stop and then wait another day to everything is get equilibrated. And so when I learned that, I was, okay, I'm glad that somebody else is doing it because I mean, I just don't have a patience for doing it. Yeah. So that was, it's amazing data. But then many other results follow. This is all ruthenium trichloride. And I'm just showing here because these are all field is x-axis. This is like our temperatures x-axis. And this group is like from Germany. And then they actually show that this is like as temperature sweeping across the nail temperature. And this line, the appearance of the quantum, the quantum conductance, the thermal conductance, quantized thermal conductance is actually happening even way beyond the Tesla. So, that is like not quantum critical point. It was like some reason, and and then this is like another group. If you look at here, if you don't look at carefully, these two data look very similar, but top is kappa XX, longitudinal thermal conductivity, and down is kappa XY. You can tell from the how much small, even the x-axis is, this is a 0 to 0.2 watts per Kelvin, but Kelvin square meter, but here, milliwatts per Kelvin square, and then even order of magnitude smaller here. So they are very similar. And then since this thermal conductivity in longitudinal thermal conductivity is dominated by phonon, and then having a very similar temperature dependence warrants that this Hall effect is thermal Hall effect is coming from the phonon. Phonon how? That's actually, there's a lot of the hand waving arguments such as Carl phonon and some skew scattering and et cetera. Okay, so these are all the things that we actually confuse ourselves. And despite of the simplicity of the concept of thermal conductivity, it is like really hard to get the very good measurement and very careful measurement, how things are done, what is important, and what you should pay attention to can be very different, right? So with this, So with this, just next 5 minutes, I'm just only glancing over how we can actually using this phonon to interpret any thermal conductivity data we have. And we are just only starting with the very simple case that there's no spin-spin interaction, completely single ion physics. So each magnetic ion, each site, spin site, can do just the spin flip transition across the Zeeman splitting in the presence of the field. And then that actually creating this type of the hybridization. And then that will actually give you field dependence of thermal conductivity. Yes. Yes. Many of them. Yeah. All right. So this whole idea is like going back to the ruthenium trichloride have this non-monotonic field dependence. Okay. So below T nail, it has that minimum position is not moving, but above, which is like kind of paramagnetic region, is actually moving out of so minimum position is moving out. So the idea, and then once the great thing about the thermal Hall effect is exciting, is everybody now start reporting this kappa XX versus field. So because in order to measure kappa XY, you must take the kappa XX as function of field as well. Okay, so I actually look at the other quantum spin liquid candidate. The common thing as an experimental point of view, quantum spin liquid candidate is there's no magnetic order. So it's all paramagnetic state, right? And look at this. This is ytterbium titanate, has a minimum. And then when you actually scale H over T, they're all merging together. And high field is like increasing. this is like cadmium chalcocite, and this also has a kind of decreasing and then increasing, but this one has some other high field phase, and then they actually doing some coming back down. But initial curve of the going down and then increasing, going down and increasing, and then those are also, and then similar to another bolide, and they also H over T is like kind of nicely characterized until system specific problem, the characteristic comes in. And so the idea is that non-monotonic kappa H as field increasing from 0 and hit the minimum, and then the minimum is increasing as functional field. How are we going to, this is like not system specific. It's a very toy model and how to do it. And that's, we actually study with this rare earth magnet, and which has a triangular radius of the ytterbium 7.5 spin. And this rare system has crystal electric field effect because of just only coming from the local Coulomb interaction. Your spin half state is actually dividing into this 4 state, and each of them, 4 state, and each of them are doubly degenerated. And when you apply field, this actually splitting, like just normal Zeeman splitting. Do you have a question?
So
Yes.
Can you go back to the
Yeah. Yeah.
Do we as the one? Yeah.
I'm sorry. Mm-hmm.
So I know that we see thermal hull and like everything we see it in silicon these days. Do you maybe this is what you're getting at? What should I expect as a theorist who hasn't? Like
I don't know. I don't know what to expect.
Is this unique
Yeah.
to the spin liquid candidates? If I
No.
hold up the materials, most materials look like this. Like
Not most material, not only quantum spin liquid material. I think we just don't have a much of understanding where the delta Ty comes from. One of the most common thing people think about is when inversion broken crystal, phonon can acquire chirality under field, and then that will actually creating the directional disperse, and then that creating the summer Hall effect. That is actually nothing to do with the magnetism.
Right.
It's just some, so for example,
I
quartz.
see it in the cuprates even.
Yeah, copper. Okay, I'm only stick to insulators.
Well, that's insulating.
Yes. Yeah. Yes. So yes, we have people has a lot of idea, and so I'm hoping that this hybridized and hybridized particle can be also part of that kind of story.
Okay.
Yeah.
Sorry to interrupt.
Oh no, I'm actually going to. So we have a paper on this one, so I'm going to. You guys can look it up. But I just want to show just one more slide. That's not what I wanted. Okay, I guess my computer just want to go to lunch. This splitting is like really quite interesting. Make the rare earth magnet interesting system, because if you go below this first excited gap, you can actually acting as this is an effective spin half system. So when we search for the quantum spin liquid material candidate, it's always the problem is very hard to find the material with a spin half spin, but these are kind of pseudo spin is spin half. And then when you apply field along the c-axis, by the way, this spectrum can be verified by all kind of spectroscopy measurement under the field. And then another thing is that you can actually apply field along the c-axis. These splittings are very, very different. And in fact, if you can look at here, there's a second order Zeeman splitting, which is actually the energy level is like proportional to h squared instead of the h. So with all this, this is like what we measured, and actually have a very non-monotonic field dependence. And the model that we have is like very simple spin phonon and spin flip excitation, and just again very simple toy model like one single mode, and diagonal term is like the spin flip excitation, and phonon, this omega naught is like display, and then this is like magnetoelastic coupling through the phonon is actually jumping back and forth. And then with this, we actually calculate very simple calculation just using this transport equation. And what we find is actually this is like pretty recover as function of temperature. Your minimum is moving out, and minimum is like getting moving out, and then this monotonic behavior can be universal to any paramagnetic state under the field. Okay, and then of course models are always getting kind of getting better. Just since your velocity, unlike the Dubai velocity, it's not constant but k dependence. Simply scattering can give you a lot improvement of the model. Bring it in. So this is like just the beginning. How spin is talking to phonon, and then maybe all this like exotic field dependence might be. We can actually start, and then again, this is also I didn't exchange energy between the magnetic at all. So starting from here, we can actually build up some more functional kind of model that kind of clear up a lot of the controversy about the data. Because once you know what answer should be, people make things get better, and then find the path to the more robust measurement. It will be a lot easier, right? So with this, I'm going to stop here. Thank you very much. Yes.
Sorry if I missed this.
Yeah.
Could you discuss a little bit how you measure the magnetic field locally on the sample?
Magnetic field is like not local on the sample. Magnetic field is like basically we'll put our sample inside of the superconducting magnet. Right? And then we know what's the range of the superconducting magnetic. And usually sample is like small enough that, because during the measurement sample is not. So it will be the same. So field is like just applied, like, like adiabatically without any costing energy of the sample. Is that what you're asking?
Yeah.
Yeah, so it's external.
I've seen that like there are data from Minoru Yamashita, and I know that for a fact they measure very carefully with like Hall sensors on the sample, depending on the history of the field and so on.
Oh, Hall sensor is like when you're changing the angle, right? So you really want to make sure the sample. So sample does not have any Hall sensor. Probably the platform. That's how I put my Hall sensor. And like summer bath, the Hall sensor is there. So when sample is rotating, because you want to know to make sure that what's the angle of that. So that's actually get the field direction out of it. Does it make so? Field is like always like one direction. Usually sample is rotating, and then with a Hall sensor to get the precision. Yes. Yeah. Yeah.
Change of temperature, is it a serious plateau, like should be high?
Thermal conductivity measurement. There's like plateau. Oh, you mean this sample? Which sample was it?
Just the trajectories. With the high.
That's okay. Yeah, that's a this one. Yeah. So what happened here? What happened here is that down here we're no heater or whatsoever, right? So hot thermometer, cold thermometer, exactly the same temperature. And then when we turn on the current, what happened is temperature gradient is like start building up. So during this is like transient, right? So once heat is like start coming in, this is like immediately get heat. It's still cold, but then heat current is like start flowing and then start leaving the sample. So then temperature gradient is established. Temperature each is all different, but temperature remaining constant because heat gradient becomes 0. So you have to wait until that point, and that time is depending on what's the heat capacity of the thermometer and all those kind of parameters like entering in. And then again, here comes steady state, reaching the steady state. Because we don't want to measure temperature around here because that's actually heat gradient is, the divergence of the heat current is non-zero in this reason.
So the delta T is the temperature difference of two different locations.
Yes.
Oh.
Yeah, one is closer to, so we assume that one-dimensional temperature profile. I mean, heat current is like mostly one-dimensional. So equitemperature line will be parallel, perpendicular just to heat current. Yes.
So what is, I didn't quite get what is the physical origin of the minimum of the.
So minimum, physical origin of the minimum, I was just going through. So at the very beginning, hybridized two hybridized mode is like actually when the H is very low, the gap is like opening up, but then that didn't change at all the rest of the spectra. And because of that, only effect you see is like that amount of the corresponding to gap is like no longer contributing the transport. So thermal conductivity goes down because it's gapping out. But then when you go to higher field, the lower band of the hybridized band become very important. So in here, this band become more and more. Upper band is no longer, it's become high energy, no longer, and then this become more and more. A lot of the large of the K particle, large lesion of the K contributing to all the heat conduction. So that actually suddenly a lot of the particle actually start, and that's why it's actually increasing as higher fields. Because of those two behaviors, you actually have to have a minimum. One is decreasing, then eventually higher field it has to increase, so you end up having a minimum. Yes.
E1. So
Yeah,
I understand these
Mhm.
cesium, as I move up on the alkalis,
Uh-huh.
I've heard that I can model this as a triangular lattice where I'm tuning J2.
Yeah.
So
Mhm.
as,
Yeah.
as I
Mhm.
go to potassium, I know people think it might be different. Do I
Yeah.
see any difference in the thermal?
So the first order answer is no. And second order answer, I mean, it's not second order. More importantly, this crystal field, electric field is like completely single ion physics. And quantum spin liquid or spin liquid physics is like completely interacting physics.
Right.
Yeah,
So but even when I
Mhm.
get to like sodium diselenium, there's no difference. Looks like the single particle.
I mean, is this up? So all those like neutron spectra and those things are taken at 50 millikelvin, where they are like really staying down here, right? And then no field dependence. So it's all right. So in here, in my energy scale, the exchange energy scale is like so small. It doesn't do anything until you go. I mean, yeah, we have so it actually, this is like completely single ion physics. Yeah. Mhm. Yes.
By shorting is it just like making the as vacuum as possible?
That's right. Yeah. Yes, as vacuum as possible. And you have to be. I mean, this is like I cannot give you any one answer. Yes, vacuum as possible. And then there's like no spurious heat leak should not be exist. I mean, it's just it's like a theorist. You guys really have to keep track of the factor 2 and plus minus sign, because depending on plus minus sign, it can be a boson and fermion, and it's a kind of same thing equivalent for physicists. You just when you have a setup, you have to be really careful about what can be possible, what kind of paths can be possible. Maybe I don't see one. So for example, when you go higher 200 Kelvin, let's say, and then you have a very tight container, as I explained, the radiation heat is like a lot. And then the radiation heat is like kind of deflected by wall and then get back shine on again on your sample. That means even though you put your heat current, I square R, just the whatever X number, but you have a lot of the radiation heat is actually constant, which is like completely random direction. It can scattered out, and then it actually hitting different ways. So resulting, if you don't take into that account, you will have a completely wrong thermal conductivity value. Well, yeah, radiation is one example, but so many, those kind of things. Yeah. Mm-hmm. Yes, one last question. Mm-hmm. What? Oh, my cryostat is helium cryostat, And my sample is always in very good vacuum. So it has a separate chamber going into inside. What do you mean by, oh, is that like helium recovery wise? Oh, this is like all liquid helium. So you have a liquid in there and you put it in, and then liquid is evaporated and collected somewhere else and then make the liquid again. I don't use, this data is not taken at the PPMS, if that's what you're asking. Yeah. Any other I'm going to stop here because everybody's hungry. I'm happy to take any question after this.